Hello everyone, welcome back to Electronics 1. The last couple of lectures we've been looking at diodes, and specifically ideal diodes, and those that behave like perfect conductors in the forward bias direction and like perfect insulators or open switches in the reverse direction. But today I want to look at diodes in a more realistic sense, and for that reason we'll call this topic real diodes. Okay, so what are the major differences between what we've looked at in an ideal diode versus what we're going to look at now being a real diode? Okay, so our ideal diodes, we assumed that there was no voltage drop in the forward direction. Maybe I'll just over here to the right here just do a quick plot of what we expected a ideal diode to how it behaved, and we said that in the forward direction it would be on with no voltage drop. In the reverse direction it would not allow any current to flow no matter what the voltage was across it. Okay, so this is not accurate for an actual real diode. There is a small voltage drop in the forward bias direction, so a small voltage drop in forward bias. Oops. Let's just make sure we're aware that that's that ideal diode. So in this forward bias condition, it does have a limit on the magnitude of reverse bias voltage it can withstand before it starts conducting. Beyond that, the diode will go into breakdown, and we'll talk a little bit more about that breakdown phenomena a bit later. And we also note from this plot of the ideal diode in the top right hand corner that in an ideal case the diode would have a infinite slope when it's in the on direction, which translates to a resistance that is zero. Okay, so in a real diode, in the forward bias, it actually has a finite slope, not an infinite slope, and therefore does have a resistance associated with it other than zero. Call this a series resistance. Okay. In fact, a real diode characteristic is exponential in nature. Okay, let's look at what the IV characteristic for a real diode looks like, and this is drawn from figure 4.7 of Sedgwick-Smith. Okay, and again, we see some of these properties we're talking about in a real diode. We see that not super obvious in this this scale. We'll look at a IV characteristic where the axes are scaled a little differently, so we can see the finer detail. But we see that there is some, however steep this might be, there is some slope to this that's not infinite. There is a breakdown region beyond which voltage, so when we exceed whatever this voltage is, which we often refer to as the breakdown voltage, in the reverse direction, the diode will actually start to conduct current. Okay, and to look at a rescaled version of that plot, here's the same diode characteristic, but with the negative voltage axis compressed and the negative current axis expanded to, as is shown here. So we've compressed this axis, so it's not of the same scale as the forward bias axis, and we've expanded this scale here to show that there is in fact some current leakage even in this region before we get into breakdown. Okay, we can describe this exponential relationship for a diode through this exponential equation, which shows that the saturation current times e to the VD, where VD is the voltage drop across the diode, divided by my ideality factor and the thermal voltage minus 1. Okay, so this is essentially the Ohm's law for diodes. Okay, and again, if we were to plot this out, we get a relationship that looked like these shown here above. Okay, what do each of these terms mean in this equation? I've stated them as I was writing them out, but IS is what's known as saturation current, sometimes also called scale current. So it's sometimes referred to as scale current. Okay, that is a function of the manufacturing process used for the diode. It can vary from diode to diode, so it's essentially comes from a specification. The thermal voltage is a quantity that's a function of Boltzmann's constant, the temperature, and the fundamental unit of charge. Okay, so this is known as the thermal voltage. Okay, and again, where K is a constant, Boltzmann's constant, which is equal to 1.38 times 10 to the minus 23 joules per Kelvin. Q, well, let's do T first. T is the temperature that the diode is operating at, and Q, we should be all familiar with, is my fundamental unit of charge, which equals 1.6 times 10 to the minus 19 coulombs. Okay, so those are all the components of the thermal voltage. N in this equation is known as ideality factor. Okay, so this is ideality factor. This is a measure of the amount of recombination that occurs in the junction region of a semiconductor. Don't worry about that too much at this point. It's going to be material dependent, so we can typically use a fixed value for a given diode, and for diodes made of silicon, the ideality factor usually falls in the range of 1 to 2, and we often use a value of 1 or 2 just for simplicity. Okay, so again, the main takeaway here is showing how the voltage across the diode relates to the current through the diode, and if we were to plot this out, so we get an expression or a relationship that looks like this shown in figures 4.7 and 4.8 from Sedgwick-Smith. In terms of kind of typical magnitudes for some of these quantities, so saturation current or scale current, we're going to see that this is tightly linked to that amount of current that leaks here in the reverse direction, often referred to it as leakage current. That said, it's a function of that saturation or scale current, which can be anywhere in the order of hundreds of nano-ohms to fractions of ohms, hundreds of nanoamps to fractions of picoamps. Okay, so clearly very small. The thermal voltage, VT, we often just use 25 millivolts as close enough for the thermal voltage at room temperature. Okay, so for most of our purposes, we'll treat the device like it's working at room temperature, and at room temperature you can do the calculation. The thermal voltage is approximately 25 millivolts. All right, let's end this lecture here. We'll keep it brief. Next lecture we will do a bit of analysis on the equation at a few different voltage levels and show how we can do some simple but modifications or simplifications to the equation for under certain operating conditions without too much sacrifice in accuracy.